Well, thanks a lot for joining. So today we're going to be talking a project we've been working with Flamand about IBM Spectrum Symphony, which is a scheduler that has been, well, is quite present, not just in the financial industry, but also in other places. The main target and the main problem with Symphony is that it was written, whatever, 30, 40 years ago and has, and doesn't really understand Kubernetes, lives in a world where it wanted stable hosts and just keeps scaling. We've tried to push it into the modern world and making sure that it can run across all cloud providers and at the starting point, at least, across a shared Kubernetes platform so that you can run it in Microsoft, in Azure, in AWS, in GCP, and even on-prem with any kube platform and run it in a scalable way. So I'll start with the interesting part, right, which is just, I'm going to start at the end with the actual numbers, right, because that's the interesting piece. What results did we manage to get and how fast did we scale? So this chart shows, right, the bottom axis is the minutes since the start of a run. We have a defined risk workload, things Monte Carlo simulations. We just run a batch of Monte Carlo simulations, mostly just for the regulators, right? They want us to run risk analysis, great. At the end of the day, it's a workload, we make CPUs do stuff. And then we see how fast, basically, can we scale up to 5,000 pods. To give you an idea, 5,000 pods is about 100,000 cores. So it starts to be quite a large workload, right? Running a singular kube cluster, and then you can pick your number, right? We did 5,000. Interesting point, could we do 50,000 or more, right? And then we'll see how we get there. And then we see, right, the progress over time. And we sort of say, well, the first attempt, the blue line here, a bit miserable, right? It took us 25 minutes for the workload to start, and then it took us, whatever, 150 minutes for it to actually scale. And then we progressively got better, right? And you see us getting better and being more and more aggressive. And that's really the interesting point, is that we now got to a point where we're able to scale what is quite a significant workload in a short amount of time, right? So if you think about this starting curve here, right, at minute 0, you've scheduled basically 16,000 cores in 3 minutes or something like that, which is really like the moment where we're starting to push scaling and pushing also all the other pieces along the line, right? So it means you're pushing your DNS, you're pushing your images, so this is all OCI containers, so you're putting your image stores, you're pushing pressure on the Kube API itself, right? And really trying to diagnose these problems as we go along, because it's not just about solving the problem, it's also making sure that we have all the observability, all the knowledge to be able to debug our problems and understand how we went from this horrid line really slow to this line in a predictable manner. So what does it look like, right? At the end of the day, we're going to start basically with an empty cluster, right? So this is OpenShift. It doesn't matter. It just needs to be a kube cluster. You can run the same thing on EKS, same thing on AKS. OpenShift just has a prettier UI than everybody else. That's really the selling point. And then we'll go and schedule workload, right? That workload is very much something like this. We're basically going to say, I want something of template Kubernetes A. Template Kubernetes A is something we predefine with the applications. They tell us, I need 16 cores, I need 64 gigs of RAM, I need this setting, I need that setting. Great, we pre-agreed this is your template. And then I say, I want 2 machines. You could say you want 100, you could say you want 5. You take your pick. And that isn't even controlled by the applications directly, it's controlled by Symphony. That schedules, that figures out, oh, I've got this amount of tasks to do, let me schedule these workloads. And then we feed it in, right? We end up saying, actually, I want to go and request those machines. And this is pure Symphony. For those who've never used Symphony, it basically gives you about a little request ID, so you can track the state of the request, and it tells you, oh, is it a successful request or not? In this case, hopefully, right, it's a successful request. We'll go and see, there we go, that the pods have now appeared back out. And that's our starting point, right? For 2, nobody cares, right? The moment you do 100, that becomes interesting. The hard part here being, really, we schedule them and we create them as cattle. So at that point, we've just said, oh, I want two of these. I could say I want 200 of these or 2,000. The hard part being, at some point, Symphony will tell you, I want to kill this very specific pod. That specific one, the C8 whatever, right? Because it knows, oh, it's finished its workload. I don't need that anymore. So we create them as cattle and then kill them as pets. And that's something Kube doesn't understand, right? Replica sets don't really do that. Stateful sets don't do that. And that's the part where in the HPC workloads, we care very much about freeing that specific workload so that then the underlying node can go away, because AWS will happily charge you for a node doing nothing, right? But we're there saying, actually, once we've killed that one, I can free the underlying node and remove the hardware. This then means that in this cluster, right, there's no auto-scaling enabled. We have a fixed pool, it's all great. And a cloud provider will typically run it on spot workloads, which means the scaler, the autoscalers, will kick in and start putting nodes underneath. So if I say I want 1,000, obviously I don't start with enough compute or nodes in my hardware to start 1,000 pods at the same time. Carpenter will say, oh, they are pods which I can't schedule. It will go away, go create the pending pods, and go from there. If we look at the workflow, because the hard part here being, when you go at that scale, the main limiting factor is your Kube API. How fast can Kube actually do things, and how asynchronous do you need to be to make sure that you're not stuck on waiting for Kube to come back? Host Factory and Symphony have very little tolerance for failure. They suppose the hardware cannot fail, and that you need to answer basically a success relatively fast. So we don't have time to call the Kube API, wait for the pods to come up. We actually have to be able to do this asynchronously and maintain the state in a separate place. So the request machines, right? That was the query I started with. It starts by calling to Host Factory in the Symphony shell. Symphony runs on shell scripts, right? It's a 90s product. It runs on shell script, and we run that. At that point, you call that little shell, and it writes the request to a working directory. This is inside the pod, right? So you have a master pod running that will write it to a working directory. At that point, you've written it to your directory on the file system. So you have kept state and you separate your concerns, right? Which means your host factory piece is completely separate to your file system. Then you run iNotify on that. So you suddenly figure out, oh, there's a new request which came in, right? With our little magic request ID generated. And then the watcher looks, oh, there's the request, and then it posts all the objects. So it says, oh, I need 2 pods, I need 10 pods, and it goes away and does a little for loop over all these things to say, let's schedule these pods. And that's the hard point, right? Kubernetes is not immediate. It takes time. You have limits, you have constraints, and you're trying very hard to make sure this doesn't stop Symphony at the other end from requesting more, right? Because Symphony will typically request 50 request machines at the same time, 50 times 100, and then call other things at the same time. And it's that separation of concerns that make the solution performant. And then, of course, at that point, right, you've posted your pod object. It goes into a pending state. Carpenter comes in, puts a node underneath, and once again, we're separating the concerns. We're saying on one side, we have the pods coming in, being created. On the other side, you're putting nodes in there. But they don't need to mix and match, right? On EKS, you're going to be saying Carpenter's the answer. On GKE, you're going to be saying custom compute classes are the answer. And it can be a completely separate process, pushing nodes and making this happen. So at that point, right, you come back with your Kube event. At some point, the pod will go, oh, I'm fully created, I'm ready. At that point, you'll write it back, right? So we have a watcher that looks at your Kube events and is able to say, oh, by the way, I saw this pod come up. And it then goes away and tells you, oh, so now I can update the status of my Symphony request. So I can go back, tell Symphony, I'm good, you've got your compute. Make sure you know about the compute and keep the life cycle of the compute, because then Symphony at the other end needs to know, oh, I need to remove my compute and go and do something else. So same thing, right? Use the same file system to synchronize your content. And then Symphony, the next request it does is a get request status. It ends up saying, oh, what's the status of the request I sent? You can control how frequently it polls, what it polls, but it polls quite aggressively. It keeps asking, oh, is my compute here? Is my compute here? Is it still here? And at that point, right, you have to answer. And instead of calling the Kube API each time Symphony's busy asking, you just check on the file system, which is obviously a lot faster and a lot more immediate than trying to wait for the maxed out Kube API because you've just pushed 5,000 pods in at the same time. So then when you come back with the answer, and you just structure the answer in the right format, right? Symphony has an expected format, and you match that format. What does it look like? So at the end of the day, when we schedule our workloads, right, we will then be able to say, let's take it out. So let's try to do that together, right? So I take my pod number, copy that number, and then say, let's generate the JSON to return the object. So host factory admin, right? That's our starting point. Host factory -admin. Let's look at the options in there, right? And we basically say, I want to request return machines. That's a Symfony term. That tells you, actually, I want to request machines to come back. And we're going to see what our options are, right? And this is matching the Symfony spec. We're not really doing anything particularly creative, right? We're just matching what the IBM spec tells you, bit of a combination of docs and retro engineering to go and figure that out, right? And this is the format you come back. Sorry, if I actually post the pod name, it will work a lot better. The downside here, right, is that you don't pick your pod name, so you have to do this dynamically. There we go. Yep. There we go. And that's your JSON coming back, right? And then you feed that into the tool to say, actually, I want to go and actually execute that command. So we're going to do host factory. Of this. Brilliant, right? And it tells you, oh, I've returned the machines. So now when we go to the cluster, we expect, there we go, right? Our pod is going down. It's terminating, you have the termination hook, and you're able to say, actually, these two were part of the same initial request, and now they can have a different lifecycle, and let Symfony manage that lifecycle independently. Symfony doesn't really know or care. It's a kube cluster. All it wants is the client to go and talk back in. Our next problem, right, is when we're running this on large scale, you end up with scaling issues. You end up with surprises of this doesn't work, this failed, Carpenter failed, EKS failed, or it worked really well and we're not sure why. And that's really one of the core features of being able to say, send it to support to be able to replay what just happened. And that's one of the really key features we've developed to be able to complain to all the different support groups internally, understand what we do, replay these very hard to replay events. And that's where we have host factory replays coming in. Let's go back in time to go and see. There we go, right? So we keep inside here an SQLite database of everything that's happening in the cluster. So all the requests coming in, all the kube events, all that sort of content. By keeping it locally, we make sure we can then export it out whenever Prometheus is ready. We don't need to wait for Prometheus to fail. We have this local backup. You can compress it, you can disable it, you can control what you want to do, but it gives you the ability to replay what happened. And so typically here, right, we're going to replay my local event. So that was the last database, right, where we created two machines somewhere, and it went away and created those two machines. So then we're able to, in the cluster, suddenly, there we go, rerun events. So replay the same runs. Symfony is a really expensive software to run, right? You need to worry about licenses, talk to IBM, which nobody really wants to do, and then go to that stage, right? And then we're able to say, actually, you don't need to run it with Symfony. Because of that separation from what host factory is doing to what Symfony is doing, we're able to say, we're able to replay events and send that across. So all you have to send across to reproduce is an SQLite database, which will tell you what happened. If we look at what's inside that SQLite database, right, it's a bunch of events, whatever happened in here. And you can see, right, we have a request of this input at this timestamp, whatever this timestamp is, for this template. And that template tells you, right, it's template Kubernetes A, and we were calling it this time, and this is the request ID, which matches up with the request ID you actually did, which then means you're able to see, can we reproduce the issue in a repeatable fashion? It's not always the case, don't get me wrong, because we're running mostly on spot compute, sometimes they're surprising in spot, right? Less availability, less capacity, you can't replay the exact thing, but you can redo the same inputs and then try them again and see, am I getting the same behavior again and again and again? Without having to pay for a Symfony license, sending it to anybody, right? You can send it to anybody and replay these pieces. So I'll pause here for any questions before I keep going. No? Brilliant. So now let's dive a bit deeper into the analytics piece of what are we trying to build And how do we compare the different runs, right? Because that becomes a really interesting question of how do we maximize pod density? Because at the end of the day, we want to use 100% of the compute that is put underneath us, right? Because that's the tipping point. You basically want to give as much compute as you can to your underlying workload. So the first thing we track, right, across runs is the distribution of CPUs, right? Across all your nodes, how much CPUs were we using on average? The interesting piece here, right, being we actually managed to get quite a lot of distribution above 100%. And we play tricks, right? We tell Cube, oh, I only want 15 cores, but then I'm going to tell Symphony, you have 16 cores. And you can tune that ratio, right, where you're playing that game of saying, I'm going to pretend you have more, because most of the time, your processors don't really need all that compute. You can tell Symphony you need more, but you don't really need it. And that's a tunable, right? You play the game, you see the percentage of failed pods, and you play that game. For CPU, relatively straightforward. For RAM, it's a lot harder, right? Because as you run out, UOM, and that's game over. So you can still play that game a bit, but you have limiting factors there. If we keep going on that sort of observability piece, right, and all that is generated from the SQLite database, we then look at what are these nodes. Sorry, so this graph is a bit complicated, but I'll walk you through it. Basically, we take our CPU utilization on each node. If you have very dark blue, it means we're basically at 100%. If you have nothing, it means you have no pods running on it. And that helps you understand what is your limiting factor, what's taking time. So typically, this white piece is the worst piece, right? You're paying for the node, you've put it in the Kube cluster, you've done the calls for the Kube API, you've paid the full price, and you've got nothing running on it. So then it begs the question, what were we doing in that section, right? And then you see it scaling, right? You see that little light blue patch at the start. Oh, I put a bit of pods in there, I'm getting better. And then I go to the really dark blue. That's fine, right? We've done a great job. This is running full schedule. We're doing really well. And then you see it ending at the other end, right? You see it slightly going into lighter shades of blue and then terminating. And the goal, obviously, is to limit these sections of light blue. That's a part of the cost, right? You can't always optimize exactly, but also, and especially, limit when nothing's happening. And that typically, that sort of ending is your carpenter settings where you're going to say, oh, after whatever, 2-3 minutes of inactivity, just kill the node if there's no pods on there. The other side here is going to be, oh, this is the Kube API maxing out. It can't place pods fast enough, so we've now maxed out the Kube API. We're a bit stuck. We need to make sure, we need to understand what's maxing out the Kube API. And you monitor that across runs, right? Here we're doing the 20 worst ones, because obviously that's your main area of interest. But then it's to understand, is it the distribution? Did we do something wrong? It's just this specific run. And then we're able to redo the same run again and see, was it just a fluke? Was it the same thing again? And then we go back to the replay feature, right? So most of the time, all our different runs across all the cloud providers this is the same workload. We run again and again and again and try to tune that workload, which is close to what should be our production workload, because then we're able to look at what do we do in production? Let me reproduce it in dev and copy that pattern. So if we keep going on the sort of observability piece, this is another interesting part of how Symphony works. Here we're diving a bit deeper into what Symphony does. Symphony has two things, right? The requests and the returns. And it basically tracks over time how many requests did Symphony put in for hardware, and then what sort of returns went in the other side. And you track that across runs, right, to make sure that you understand what's happening. Some runs go well, some runs don't, right? So typically, if we take this run, it basically means there's 5,000 requests, right, because we're scaling to 5,000 pods. We max that out. Then you see a bit of eviction floating around here as things come out, and you reschedule it on the other side with new requests coming in. Because as pods get evicted, then Symphony is there telling you, oh, I'm missing compute, I need a bit more compute. Let me go and schedule a bit more pods in there. And so that's the sort of game we play, right? Because of course, you're running on spot, you get a certain eviction rate. And you see that's the sort of moment where we got evictions. That helps you figure out, was it reproducible? Was it caused by spot eviction? Was it caused by something else? And it helps you solve that sort of problem. Let's keep going, right? So then we keep monitoring the sort of number of nodes, right? Because that's another interesting piece. Do you have a correlation between your node types and your failures? And sometimes you do, right? Sometimes there are links where you've misconfigured something on large nodes and it goes wrong. So typically one of our failures was on the extremely large nodes, we hadn't put a big enough root disk, and we have a stable root disk size across all the node types. Well, guess what? You fill in your disks really fast when you run 25 pods compared to 5 pods. And so you learn that lesson that, oh, these node types are really, really problematic or not. And we can tune that, adapt that. The nice part here, right, is that it also helps us make things reproducible in the sense that now we know what node types were we using for that run, and is there a link to the failure rates, right? And we're using here a stupidly large spectrum, right? We don't care. In this workload, silicon is silicon. It doesn't care what the underlying compute type is. And whatever, right? Carpenter somehow picked 20 different types, and according to the request coming in. But we don't care in this workload. You might care, you might tune it, but that's really a separate concern, and we leave that to the cloud providers. So we separate ourselves out from the Kubernetes, the custom compute classes. We just don't want to deal with that separately. We make sure we're not involved in that. We track it, but we don't really care. If I keep going, node provisioning time. So that's a really interesting question, right? Between your runs and between cloud providers, we then need to be able to compare node provisioning times, right? How long did it take from the moment we ask a node to join the cluster for it to be ready? So we can't track before it joins the cluster, right? That's not in the kube event. That's the point. We only track it when it comes in. We should track it before. We're working on that piece, but we're really tracking the moment it joins the cluster, how long does it take it to be ready? And that's basically mostly based on what daemon sets are you running in there? Are you running your own custom AMIs? Are you doing things like that? And then you're able to put a value on that. How much is it costing us to do these setups? And then it becomes a conversation with our security teams saying, oh, do you think this daemon set adds enough value to justify that? How could we optimize that? Because that here, when we're saying 14 seconds, I can guarantee you that the first run was not 14 seconds, it was in the couple of minutes to get something running, right? And we've optimized that over time, and tracking that really brings a lot of value to us. The next piece, right, is what does the business see? Because the key KPI here, the business does not care what the node startup time is, right? They have zero interest in practice of figuring out, does it matter or not? The only thing they see is how fast do my requests complete? How fast when I put workload into Symphony, well, how long until I actually get it running and how much until it's executed? And this is where we track it over time, right? This is a box plot, and we're basically saying when we request hardware, it takes you, what, an average of 120 seconds to get your compute. Was it better in the other run or not, right? And that's an interesting question. We went to tune that run, 550 seconds. We obviously did something wrong. What changed? And then we go down that route of understanding what changed. We do the same thing for the returns, right? Because there's two important parts here. You've started up your compute really fast, your workload's running, it's going great, and then suddenly the workload's ended, well, you're still paying for the hardware, and at that point we need to get really good at tracking what went wrong. How do we make sure that we drop this hardware as fast as you can the moment we don't need it anymore? So then the next thing we're going to track is basically the pods. So the pods are an interesting question, right? It's how much time does it take you to schedule a pod from it's now placed on a node and it's ready to actually be doing something useful for the whole workload, right? So you go from created to scheduled. That's mostly driven by Carpenter, right? This first run, pretty bad, right? It took us 1,000 seconds to get a pod running. Something's going wrong, right? It takes you 20 minutes to get a pod scheduled onto a node. We've messed up somewhere. But then scheduled to running, that's much better, right? Suddenly we're in a much better state. And then you can see us improving over time, right? We're then able to say, actually, in future runs, we need to improve that piece and go and figure out what went wrong. And we keep track of that and have live metrics of that happening. The next piece we start looking at is CPU over lifetimes, right? So your CPU utilization over the lifetime of the node. Is there a moment where nodes struggle to come up at the start, right? So on the bottom line, we have the node lifetime. How long did we have the node in the cluster when it was running? On the other axis, we've got the average CPU utilization. How much CPU was that node used for over that period? Some of them, right, are pretty bad. You have this little batch at the bottom here saying, actually, they joined the cluster and they got evicted straight away. And that's just about the worst case, right? You've done all the work, you put the pod on it, you've paid all the Kube API costs, you've got all the setup, and then you get the spot eviction. And that means, in practice, we get 0% utilization out of that. That's one of the costs of doing spot, right? You get evicted now and again. And then you have this massive batch, right, where it went really quite well, right? You got 200% utilization, and they keep going, and they keep running 100%. But then we start asking questions, right? This middle line at 50%, that node had all the time in the world to pick up more workloads. Why did it not? What did we do wrong? And that's the really interesting question, right? Where we keep digging into the numbers to try and understand what did we do wrong, what should we change? And this is across runs. Right? So you'll have runs, right, which are better, right? That run, very different structure. We tune Carpenter, very different structure. Suddenly you have a lot less zeros, right? And we're a lot less sort of, oh, the run lasted basically 45 minutes, and it was just sort of that sort of batch. It begs a question, can we move that batch up slightly, get to 100% or not? And we keep working on that to try and move our cloud of points to different places. So now the last piece I'm going to talk about is really the average cost of our run, right? So the vCPU hours. How much did you pay for your same workload, right? Because we rerun the same workload again and again and again. So typically here, right, run 9 did a really good job at vCPU hours. And that's what we pay for at the end of the day, right? This is the same workload. We keep rerunning to try and optimize it. 33,000 hours. Great story, right? We did really well. The next run, where we saw the 1,000 seconds to bring up a pod, well, guess what? We managed on the same workload, just by tuning our Carpenter setup, to drop that by 30,000 hours. That's a 50% reduction in cost, right? Just because we're tuning that in a slightly different way. And that shows really the importance of playing that game, of trying to understand what our drivers are and which part of the lifecycle of the pods and the nodes we're trying to optimize. So I think this is the end of my time. Thanks a lot for your attention, and do come to me for any questions. Thank you.